Okay, so question 1. The following diagrams show the structure of diamond, graphite and carbon nanotubes. 2 of the structures shown above conduct electricity. Name both and give the reason that they're able to conduct electricity. So these are 3 allotropes of carbon, allotropes being different physical forms of the same element. And so to answer the question, the structures that are able to conduct electricity are graphite and carbon nanotubes. And the reason for that is that they both have delocalized electrons. So their structure contains delocalized electrons. And because they're delocalized and electrons, they can move and they are charged, so they can carry current. So these are the delocalized electrons here, and then the delocalized electrons in the nanotube are not really visible because it's quite a complex structure, but each carbon atom only bonds to 3 other carbon atoms, leaving one of its outer shell electrons available for delocalization. Okay, name the structure above that is used as a lubricant and give a reason why it is suitable for this use. So again, that's graphite, and it's because the carbon sheets, okay, so these are the sheets here, and these are the delocalized electrons. The carbon sheets can slide over each other due to the weak bonding formed by the delocalized electrons. Okay, now this part of it is not strictly on our syllabus, but it's mainly the calculation that I chose this for. So the reaction of chlorine with iron can be demonstrated using the following apparatus. So we've got chlorine gas being blown into this tube over some iron wool, and the whole thing is heated. State why the reaction should be carried out in a fume cupboard. Well, that's because chlorine is toxic. And then the product of the reaction above is iron 3 chloride. Complete and balance the following simple equation for the reaction. Okay, so we know that we've got chlorine gas and iron. So if we start off with the iron, and then chlorine gas, what you need to know here is that chlorine gas is a diatomic molecule, so that's Cl2, and then from there on in it's a matter of balancing the equation. So we can see here we've got 3 chlorines in the FeCl3, so it's always a good idea to make this an even number. So if we tentatively put a 2 there, that will give us 6 chlorines on this side, so we'll need 3 here. Okay, and by doing that, it means we'll need 2 ions here, so that's a finished product. Okay, so we'll just double check: 2 ions, 6 chlorines altogether. 2 times 3 is 6 chlorines altogether. Okay, so this next question, calculate the percentage biomass of chlorine in iron 3 chloride. Okay, so this is definitely something you might be expected to do, as is the balance in the equation. Okay, so in iron 3 chloride there are 3 chlorines. Okay, so to calculate the percentage by mass, we would need to do 3 times 35.5. That's the mass of chlorine, and then if we divide that by the mass of the whole molecule, okay, which would be 56 plus the 3 times 35.5, because that would be the mass of the formula FeCl3, and then we would multiply that by 100 once we've got an answer. So if we resort to our trusty calculator, so we've got the 3 times 35.5 equals 106, and then we're going to divide that by 56 plus 3 times 35.5, which of course I could have replaced with the 106.5, but there we go. And then that's times 100 gives us 66%. So 65.5 is 66%. So 66% of iron 3 chloride is chlorine. Okay, moving along now. I did put this QWC question in. So thermochromic pigments, photochromic pigments, and shape memory alloys are types of smart material. Describe your understanding of smart materials. Your answer must include what is meant by smart material and some examples of smart materials, their special properties and uses. So if we just take the first, we're given 1, 2, 3 different smart materials in the question, so it would be wise to take those as examples. There's 6 marks for this question. We need to come up with some examples, but their properties. So we need first of all establish what is meant by smart material. So a smart material is one that responds physically to changes in its environment, including temperature, light level, pH, and saturation of water. I'm thinking of polymers there. Saturation of water. Okay, so that would sort of give a description of what they are in general, and then it asks us for examples. So, for example, thermochromic pigments can be used in forehead thermometers. Okay, so you get these strips that you can place on your forehead to tell you your forehead. I can't write thermometers. Strips you put on your forehead that tell you your temperature. That would be thermochromic pigments. We've got photochromic pigments. And they've been used for many years in light-sensitive glasses. And then shape memory alloys can be used in so-called indestructible glasses frames. Indestructible glasses frames. So if they get bent, if you sit on them, you place them in hot water usually, and then they pop back into shape because they remember the shape they should be in. Okay, so between the description and the 3 examples with uses there, as long as you write it well, we should be looking at the 6 marks. Okay, number 4. When lithium reacts with chlorine, lithium chloride is formed. Give the electronic structure of lithium and chlorine. Okay, so, and I remember to put a periodic table on the back of this. We would have looked at that, and we would have found that lithium has atomic number 3. Okay, and with its atomic number 3, its electronic structure is 2, 1. Chlorine has an atomic number of 17, so it's 2, 8, 7. So use the electronic structures above to draw diagrams to show the transfer of electrons and the formation of ions that occur as lithium chloride is formed. So we don't need to recognize which type of diagram we draw here because it tells us the formation of ions, so we know it's the ionic bonding diagram. So if we start over on the left to give us room to show what happens next, if we start with the lithium, lithium has got 1 electron in its outer shell. Okay, so we can get away with just drawing that single outer shell. Okay, we don't need to draw the inner one, although if you're more comfortable doing that, it's not wrong. It just makes the diagram more complex. Chlorine has 7 electrons in its outer shell, and again, we don't need to draw the inner shells for this sort of diagram. And so the question says, draw the diagram to show how the transfer of electrons and the formation of the ions can occur. So the transfer of electrons is shown by an arrow going from that electron there to the shell of the chlorine. As a result of that process, we end up with a lithium ion. Okay, now because we've not drawn the inner shells, we can just draw that. And as a result of losing 1 electron, it becomes positive. And then the chloride ion, because of course when non-metals become ions, they subtly change their name to "ide", so this becomes the chloride ion. And we just make it clear that that extra electron there has come from the fluorine, from the lithium rather. Because it's gained an electron, it becomes minus. Okay, so we've got the electronic structures, we've shown the transfer of electrons, and we've shown the formation of the ions that occur, making sure that we put in the charges. Okay, oxygen has an electronic structure of 2,6. Use the information to draw a diagram to show the bonding in a molecule of oxygen. Okay, so the clue here is it's a molecule, but also that we've only got non-metals. So this time it's not the ion formation type of diagram, it's the sharing of electrons type of diagram. And what we need to remember about oxygen is that it needs 2 electrons to get a full outer shell. So consequently, we need to share 2 pairs. So we need a reasonable space for the overlap. So it's probably best to draw the electrons first, making sure that those 4 electrons, 2 crosses and 2 dots, appear on the overlap. So each atom has 6 electrons in its outer shell. We've drawn 2 already. So on this side, we'll draw another 4 crosses. On this side, we'll draw another 4 dots. Okay, so each atom individually has 6 electrons, but overall they share 8. Now, lithium chloride is solid at room temperature, whereas oxygen is a gas. Name the type of bonding present in each substance and explain the difference in their state at room temperature. So, lithium chloride exhibits ionic bonding with very strong electrostatic forces. Okay, so the forces are due to the oppositely charged ions. So we can refer to that as electrostatic forces. So that's why it's got a high melting point. And then the intermolecular forces between oxygen molecules are weak. So I can just illustrate that with a diagram. So these forces here are weak, whereas the bonds within the molecule are strong. But it is the weak bonds between molecules that mean that oxygen gas has got a low melting point and boiling point. Okay, moving on to this question, which is from your organic section part of the syllabus. The following diagram shows some reactions of ethene. So we need to remember that ethene is a 2-carbon molecule with a double bond. So that's 2 carbons, and the ene bit is double bond. And so we've got here reaction A, where the double bond disappears to be replaced by hydrogen. Then reaction B, which shows the polymerization of ethene. These square brackets with the bonds extending out beyond the square brackets, and the N there tells us that this is a polymerization reaction. And then coming down here, we've got the addition of bromine water, which is the classic test for ethene. So bromine water is a browny orange color, and when it reacts with a molecule with a double bond in it, that browny orange color, it decolorizes, it goes away. Okay, so complete the diagram by giving the missing structure. So bromine water contains Br2 molecules. The double bond opens up, and one bromine atom attaches to each side of the double bond, or in other words, to each carbon. So we could draw Br, C, C, Br, and then above and below we've got the hydrogens that were there in the first place. And so what's happened here is if we've saturated the molecule, okay, there's no longer a double bond. All the carbons have 4 bonds going to different atoms. Describe what would be seen during the reaction between ethene and orange bromine water. So the orange colour would decolorize, which is the technical term, decolorize. And then give the name of the types of reaction in A and B. Okay, so A is hydrogenation or reduction. Okay, we can call it reduction. Hydrogenation. We even call it saturation. It's many names because you're saturating the double bond. And then B is polymerization. So you need to be able to recognize that that format there with the square brackets and the bonds extending either side of the square brackets. Okay, copper is an important metal in everyday life. It can be produced from its oxide by heating with carbon. The equation for the reaction is shown below. So you've got 2 copper oxide molecules reacting with carbon to form 2 copper atoms and carbon dioxide. Okay, so this is an example of a reduction reaction from the point of view of the copper oxide, and an oxidation reaction from the point of view of the carbon. So use the equation to calculate the maximum mass of copper that could be produced when using 1.5 tons of carbon. So the equation tells us that for every 1 ton or 1 gram or 1 kilogram of carbon, sorry, not ton, kilogram, 1 atom, start again. The reaction tells us that for every 1 atom or mole of carbon, we need 2 moles of copper oxide. And the question, let's just make sure we get this question right. The maximum mass of copper that could be produced, okay. And also we get 2 lots of copper. So for every mole or molecule of copper, we get 2. I'm having a nightmare here. For every mole of carbon, we get 2 moles of copper. That's the information we need from the equation. So what we need to do is work out how much carbon there is in 1.5 tons, and then we can double it in terms of moles, and then we multiply that by the MR of copper, and that'll give us the mass. So we've got 1.5 tons of carbon. If we divide that by 12 tons per mole, that's not strictly accurate, however the units will work because tons will cancel, and if you divide by something that's divided by it, it comes to the top. So if we do the 1.5, hey mouse, come on mouse, we hide him. Okay, so 1.5 divided by 12 gives us 0.125, so that's 0.125 moles. Okay, now the purist out there will say it's not actually moles because we're using tons and not grams, but the numbers will work. So if we've got 0.125 moles of carbon, because we've taken that value from the tons of carbon, then from the equation we need to double that, because for every single mole of carbon we use, we make 2 moles of copper according to the equation. So if we multiply that by 2, so 0.125 moles times 2 equals 0.25 moles of copper, but we don't want to know the number of moles of copper, we want to know the number of tons. So if we further multiply that value by the AR of copper, which for the purposes of this calculation is 64 tons per mole. So if we look at the units, mole divided by mole, well, they will cancel. I'll leave it as an answer in tons, okay? And a quarter of a ton is 16, okay? So 16 tons of copper. Okay, which seems a little high, but given that we've got twice as much copper produced and the MR of copper is 4 times that of carbon, then that would explain that away. Okay, so for every 1.5 tons of carbon, you make 16 tons of copper. Okay, when the reaction was carried out using 1.5 tons of carbon, it was found that the yield of copper was only 12 tons. Calculate the percentage yield for the reaction. Okay, so that verifies basically that we've got the correct answer, because this value is in the right order of magnitude, the right sort of size, but it is lower, and that's due to losses along the way. So the yield is how much you did make compared to how much you should have made. So the 12 tons comes from the question, and the 16 tons comes from our previous calculation. And that there, and I think it's 75%, but we'll go through the motions. So 12 divided by 16, 0.75, which is 75%. Okay. Okay, this next one now, given that these were from papers from different years, a little bit of repetition here, but this is the electronic structure of calcium, fluorine, and phosphorus are as follows. Draw a dot and cross diagram to show the transfer of electrons and formation of ions. Yes, calcium reacts with fluorine to make calcium fluoride. Okay, so from our we've got dot and cross, but we're told it's a transfer of electrons diagram. Okay, so it's not a sharing diagram. Okay, we've got calcium at 282 and fluorine at 27. So as before, we don't need to draw all the shells. Okay, we can get away with drawing calcium with 2 electrons to represent the 2 electrons in the outer shell, and then fluorine has got a configuration of 2, 7. So if we draw 1, 2, 3, 4, 5, 6, 7, we can see that fluorine actually only needs 1 electron to get a full outer shell. So if that electron there is transferred to fluorine, there is no more room in this fluorine for that electron. So consequently, we do need a second fluorine atom to make this work. So 1, 2, 3, 4, 5, 6, 7. So that electron goes down to there. And then we need to show the other side of the story. So when this calcium loses 2 electrons, it becomes Ca2+, because it's lost 2 negative electrons. And then the fluorines become fluoride, because when a non-metal becomes an ion, changes its name slightly. Okay, so we just show that electron from the calcium, but each one is only singly negatively charged because it's only gained 1 electron. And so this one is also negatively charged. So the formation of ions as calcium reacts with fluorine to form calcium fluoride. So we've shown the transfer, and we've shown what has been created, and we've made sure we've put the charges in the final diagram. Draw a dot and cross diagram to show the bonding in a molecule of phosphorus trifluoride. Okay, so this time there's no transfer electrons because both elements involved in this bonding are non-metals, so this must be a covalent bonding diagram, a shared electron bonding diagram. Now this one isn't one that we would necessarily practice, however, the principles are the same. So phosphorus is 285, so we can again just draw the outer shell. So if it's got 5 electrons, it's going to have 2 of them in a pair, and then the other 3 are going to be available for bonding with another atom. And in this case, that atom is fluorine. So we make sure that we overlap. And we've already established that fluorine has got 7 electrons in its outer shell. So that 7th electron there overlaps here. And then the same is true of another fluorine. So 1, 2, 3, 4, 5, 6, 7, and then finally 1, 2, 3, 4, 5, 6, 7. So each atom has now got a share of 80 electrons, starting with their own original complement. Okay. A hydrocarbon was found to contain 0.96 grams of carbon and 0.2 grams of hydrogen. Calculate the simplest formula for this hydrocarbon. You must show you're working. Okay, so this is an empirical formula question. Okay, so the way I to do it is one column is the operation, and then the other column, other columns are for the elements that were given. I realise I've not really planned this very well. So I've got the mass given in the question. So for carbon it's 0.96, and for hydrogen it's 0.2. Okay. That's grams. Okay. So the first thing we do is we divide by the AR. Okay, so for each one, so 0.96 divided by 12 gives us 0.08, and then 0.2 divided by 1 is 0.2. And if we divide by the smallest, which is the thing we need to remember, of these two values, that's going to be 1, and then 0.2 divided by 0.08, 0.08 is 2.5. You can't have 2.5 atoms, okay, so we'll need to double both of these, so we get C2H5, which is interesting. C2H5. Okay, so that's the end of that then.